Learning objectives. In this chapter, the user will learn the following in detail. Concepts of data warehouse, difference between operational database system and data warehouse, multi-dimensional data model, data cube, stars, snowflakes, fast schemes for multi-dimensional database, measures, concept hierarchies, OLAP operation on multi-dimensional data model, data warehouse architecture, types of OLAP servers, life cycle of data warehouse implementation, relationship between data warehouse and data mining. Introduction. Data warehouses generalize and consolidate data in multidimensional space. The construction of data warehouse involves data cleaning, data integration, and data transformation, and can be viewed as an important pre-processing step for data mining. Moreover, data warehouses provide online analytical processing (OLAP) tools for the interactive analysis of multidimensional data of varied granularities, which facilitates effective data generalization and data mining. Many of the data mining functions such as association, classification, prediction, and clustering can be integrated with OLAP operations to enhance interactive mining of knowledge at multiple levels of abstraction. Hence, a data warehouse has become an increasingly important platform for data analysis and OLAP and will provide an effective platform for data mining. This chapter presents an overview of data warehouse and OLAP technology. This overview is essential for understanding the overall data mining and knowledge discovery process. Concept hierarchies. A concept hierarchy defines a sequence of mappings from a set of low-level concepts to a high-level, more general concepts. Consider a concept hierarchy for the dimension location. City values for location include Vancouver, Toronto, New York, and Chicago. Each city, however, can be mapped to the province or state to which it belongs. For example, Vancouver can be mapped to British Columbia and Chicago to Illinois. The provinces and states can in turn be mapped to the country, example, Canada or United States, to which they belong. These mappings form a concept hierarchy for the dimension location, mapping a set of low-level concepts, that is cities, to a higher level, more general concepts, that is countries. This concept hierarchy is illustrated in the Many concept hierarchies are implicit within the database schema. For example, suppose that the dimensions location is distributed by the attributes number, street, city, province or state, zip code and country. These attributes are related by a total order, forming a concept hierarchy such as street, which belongs to city, which belongs to province, or state, which belongs to country. Alternatively, the attributes of a dimension may be organized in a partial order, forming a lattice. An example of a partial order for the time dimension based on the attributes day, week, month, quarter, and year is: day is part of a month, part of a quarter, part of a week, part of a year. Likewise, week is a part of the year. A concept hierarchy that is the total or partial order among attributes in a database schema is called a schema hierarchy. Concept hierarchies that are common to many applications, for example, for time, may be predefined in the data mining system. Data mining systems should provide users with the flexibility to tailor predefined hierarchies according to their particular needs. For example, users may want to define a fiscal year starting on April 1 or an academic year starting on September 1. Concept hierarchies may also be defined by discretizing or grouping values for a given dimension or attribute, resulting in a set grouping hierarchy. A total or partial order can be defined among groups of values. An example of a set grouping hierarchy for the dimension price, where an interval $X going up to $Y denotes the range from $X exclusive to $Y inclusive. There may be more than one concept hierarchy for a given attribute or dimension based on different user viewpoints. For instance, a user may prefer to organize price by defining ranges for inexpensive, moderately priced, and expensive. Concept hierarchies may be provided manually by system users, domain experts, or knowledge engineers, or may be automatically generated based on statistical analysis of the data distribution. Figure shows hierarchical and lattice structures of attributes in warehouse dimensions. A hierarchy for location, and B, a lattice for time. Figure shows a concept hierarchy for price. Concepts of data warehouse. Data warehouse. A data warehouse refers to a data repository that is maintained separately from an organization's operational databases. Data warehouse systems allow for integration of a variety of application systems. They support information processing by providing a solid platform of consolidated historic data for analysis. A data warehouse is a subject-oriented, integrated, time-variant, and non-volatile collection of data in support of management's decision-making process. The four keywords subject-oriented, integrated, time-variant, and non-volatile distinguish data warehouses from other data repository systems such as relational database systems, transaction processing systems, and file systems. Let's take a closer look at each of these key features. Subject-oriented. A data warehouse is organized around major subjects such as customer, supplier, product, and sales. A data warehouse focuses on the modeling and analysis of data for decision makers. Data warehouse typically provide a simple and concise view of particular subject issues by excluding data that are not useful in the decision support process. Integrated. A data warehouse is usually constructed by integrating multiple heterogeneous sources, such as relational databases, flat files, and online transaction records. Data cleaning and data integration techniques are applied to ensure consistency in naming conventions, encoding structures, attribute measures, and so on. Time variant. Data are stored to provide information from an historic perspective, example, the past 5 to 10 years. Every key structure in the data warehouse contains either implicitly or explicitly a time element. Non-volatile. A data warehouse is always a physically separate store of data transformed from the application data found in the operational environment. Due to this separation, a data warehouse does not require transaction processing, recovery, and concurrency control mechanisms. It usually requires only two operations in data accessing: initial loading of data and access of data. A data warehouse is a semantically consistent data store that serves as a physical implementation of a decision support data model. It stores the information an enterprise needs to make strategic decisions. Data warehouse is an architecture constructed by integrating data from multiple heterogeneous sources to support structured and/or ad hoc queries, analytical reporting, and decision-making. Data warehousing is a process of consulting and using data warehouses. The construction of data warehouse requires data cleaning, data integration, and data consolidation. The utilization of data warehouse often necessitates a collection of decision support technologies. Many organizations use this information to support business decision-making activities, including increasing customer focus, which includes the analysis of customer buying patterns such as buying preference, buying time, budget cycles, and appetites for spending. Repositioning products and managing product portfolios by comparing the performance of sales by quarter, by year, and by geographic regions in order to fine-tune production strategies. Analyzing operations and looking for sources of profit. And managing customer relationships, making environmental corrections, and managing the cost of corporate assets. The traditional database approach to heterogeneous database integration is to build wrappers and integrators or mediators on top of multiple heterogeneous databases. When a query is posed to a client site, a metadata dictionary is used to translate the query into queries appropriate for the individual heterogeneous sites involved. These queries are then mapped and sent to local query processing. The results returned from different sites are integrated into a global answer set. This query-driven approach requires complex information filtering and integration processes and competes with local sites for processing resources. It is inefficient and potentially expensive for frequent queries, especially queries requiring aggregations. Data warehousing provides an interesting alternative to this traditional approach. Rather than using a query-driven approach, data warehousing employs an update-driven approach in which information from multiple heterogeneous sources is integrated in advance and stored in a warehouse for direct querying and analysis. A data warehouse brings high performance to the integrated heterogeneous database system because data are copied, pre-processed, integrated, annotated, summarized, and restructured into one semantic data store. Furthermore, query processing in data warehouses does not interfere with the processing at local sources. Moreover, data warehouses can store and integrate historic information and support complex multidimensional queries. Data warehouse architecture. Multi-tiered architecture data warehouses often adopt a three-tier architecture. The bottom tier. It is a warehouse database server that is almost always a relational database system. Back-end tools and utilities are used to feed data into the bottom tier from operational databases or other external sources. For example, customer profile information provided by external consultants. These tools and utilities perform data extraction, cleaning, and transformation. For example, to merge similar data from different sources into a unified format, as well as load and refresh functions to update the data warehouse. The data are extracted using application program interfaces known as gateways. A gateway is supported by the underlying DBMS and allows client programs to generate SQL code to be executed at a server. Examples of gateways include ODBC, Open Database Connection, and OLEDB, Object Linking and Embedding Database by Microsoft, and JDBC, Java Database Connection. This tier also contains a metadata repository which stores information about the data warehouse and its contents. The middle tier. It is an OLAP server that is typically implemented using either a relational OLAP ROLAP model, that is an extended relational DBMS that maps operations on multidimensional data to standard relational operations, or a multidimensional OLAP MOLAP model, that is a special purpose server that directly implements multidimensional data and operations. The top tier is a front-end client layer, which contains query and reporting tools, analysis tools, and or data mining tools, that is, trend analysis, prediction, and so on. Differences between operational database systems and data warehouses. The major task of online operational database systems is to perform online transaction and query processing. These systems are called Online Transaction Processing (OLTP) systems. They cover most of the day-to-day operations of an organization, such as purchasing, inventory, manufacturing, banking, payroll, registration, and accounting. Data warehouse systems, on the other hand, serve users or knowledge workers in the role of data analysis and decision-making. Such systems can organize and present data in various formats in order to accommodate the diverse needs of different users. These systems are known as Online Analytical Processing (OLAP) systems. The major distinguishing features of OLTP and OLAP are summarized as follows. Users and system orientation. An OLTP system is customer-oriented and is used for transaction and query processing by clerks, clients, and information technology professionals. An OLAP system is market-oriented and is used for data analysis by knowledge workers, including managers, executives, and analysts. Data contents. An OLTP system manages current data that typically are too detailed to be easily used for decision-making. An OLAP system manages large amounts of historic data, provides facilities for summarization and aggregation, and stores and manages information at different levels of granularity. These features make the data easier to use for informed decision-making. Database design. An OLTP system usually adopts an entity relationship (ER) data model and an application-oriented database design. An OLAP system typically adopts either a star or a snowflake model and a subject-oriented database design. View. An OLTP system focuses mainly on the current data within an enterprise or department without referring to historic data or data in different organizations. In contrast, an OLAP system often spans multiple versions of a database schema due to the evolutionary process of an organization. OLAP systems also deal with information that originates from different organizations, integrating information from many data stores. Because of their huge volume, OLAP data are stored on multiple storage media. Access patterns. The access patterns of an OLTP system consist mainly of short, atomic transactions. Such a system requires concurrency control and recovery mechanisms. However, accesses to OLAP systems are mostly read-only operations, because most data warehouses store historic rather than up-to-date information, although many could be complex queries. Table shows the comparison of OLTP and OLAP systems. Life cycle of data warehouse implementation. Data warehouses implementation. Data warehouses contain huge volumes of data. OLAP servers demand that decision support queries be answered in the order of seconds. Therefore, it is crucial for data warehouse systems to support highly efficient cube computation techniques, access methods, and query processing techniques. In this section, we present an overview of methods for the efficient implementation of data warehouse systems. Explore how to compute data cubes efficiently, how OLAP data can be indexed using either bitmap or join indices, how OLAP queries are processed, various types of warehouse servers for OLAP processing, efficient data cube computation and overview. At the core of multidimensional data analysis is the efficient computation of aggregations across many sets of dimensions. In SQL terms, these aggregations are referred to as group bys. Each group by can be represented by a cuboid, where the set of group bys forms a lattice of cuboids defining a data cube. In this subsection, we explore issues relating to the efficient computation of data cubes, the compute cube operator, and the curse of dimensionality. One approach to cube computation extends SQL so as to include a compute cube operator. The compute cube operator computes aggregates over all subsets of the dimensions specified in the operation. This can require excessive storage space, especially for large number of dimensions. We start with an intuitive look at what is involved in the efficient computation of data cubes. Figure shows a lattice of cuboids making up a 3D data cube. Each cuboid represents a different group by. The base cuboid contains city, item, and year dimensions. The base cuboid contains all three dimensions, city, item, and year. The base cuboid is the least generalized, most specific of the cuboids. The apex cuboid is the most generalized or least specific of the cuboids and is often denoted as all. If we start at the apex cuboid and explore downward in the lattice, this is equivalent to drilling down within the data cube. If we start at the base cuboid and explore upward, this is akin to rolling up. An SQL query containing a no group by, example, compute the sum of total sales, is a zero-dimensional operation. An SQL query containing one group by, for example, compute the sum of sales group by city, is a one-dimensional operation. A cube operator on n dimensions is equivalent to a collection of group by statements one for each subset of the n dimensions. Therefore, the cube operator is the n-dimensional generalization of the group by operator. Online analytical processing may need to access different cuboids for different queries. The storage requirements are even more excessive when many of the dimensions have associated concept hierarchies, each with multiple levels. This problem is referred to as a curse of dimensionality. For an n-dimensional data cube, the total number of cuboids that can be generated, including the cuboids generated by climbing up the hierarchies along each dimension, is the total number of cuboids equals pi, that is product of ranging from I equals 1 to n, into Li plus 1, where Li is the number of levels associated with dimension I. 1 is added to Li in the equation to include the virtual top level all. Note that generalizing to all is equivalent to the removal of the dimension. This formula is based on the fact that at most one abstraction level in each dimension will appear in a cuboid. Partial materialization, selected computation of cuboids. There are three choices for data cube materialization given a base cuboid. No materialization. Do not pre-compute any of the non-base cuboids. This leads to computing expensive multi-dimensional aggregates on the fly, which can be extremely slow. Full materialization. Pre-compute all of the cuboids. The resulting lattice of computed cuboids is referred to as the full cube. This choice typically requires huge amounts of memory space in order to store all of the pre-computed cuboids. Partial materialization. Selectively compute a proper subset of the whole set of possible cuboids. Alternatively, we may compute a subset of the cube which contains only those cells that satisfy some user-specified criterion, such as where the tuple count of each cell is above some threshold. We will use the term subcube to refer to the latter case, where only some of the cells may be pre-computed for various cuboids. Partial materialization represents an interesting trade-off between storage space and response time. The partial materialization of cuboids or subcubes should consider three factors. 1. Identify the subset of cuboids or subcubes to materialize. 2. Exploit the materialized cuboids or subcubes during query processing. And 3. Efficiently update the materialized cuboids or subcubes during load and refresh. The selection of the subset of cuboids or subcubes to materialize should take into account the queries in the workload, their frequencies, and their accessing costs. In addition, it should consider workload characteristics, the cost for incremental updates, and the total storage requirements. The selection must also consider the broad context of physical database design, such as the generation and selection of indices. Several OLAP products have adopted heuristic approaches for cuboid and subcube selection. A popular approach is to materialize the cuboid set on which other frequently referenced cuboids are based. Alternatively, we can compute an iceberg cube, which is a data cube that stores only those cube cells with an aggregate value, for example, count that is above some minimum support threshold. Another common strategy is to materialize a shell cube. This involves pre-computing the cuboids for only a small number of dimensions, that is 3 to 5 of a data cube. Queries on additional combinations of the dimensions can be computed on the fly. Once the selected cuboids have been materialized, it is important to take advantage of them during query processing. This involves several issues, such as how to determine the relevant cuboids from among the candidates' materialized cuboids, how to use available index structures on the materialized cuboids, and how to transform the OLAP operations onto the selected cuboids. Finally, during load and refresh, the materialized cuboids should be updated efficiently. Parallelism and incremental update techniques for this operation should be explored. Indexing OLAP data, bitmap index and join index. To facilitate efficient data accessing, most data warehouse systems support index structures and materialized views using cuboids. The bitmap indexing method is popular in OLAP products because it allows quick searching in data cubes. The bitmap index is an alternative representation of the record ID RID list. In the bitmap index for a given attribute, there is a distinct bit vector BV for each value V in the attribute's domain. If a given attribute's domain consists of n values, then n bits are needed for each entry in the bitmap index. There are n bit vectors. If the attribute has the value V for a given row in the data table, then the bit representing that value is set to 1 in the corresponding row of the bitmap index. All other bits for that row are set to 0. Bitmax indexing is advantageous compared to hash and tree indices. It is especially useful for low cardinality domains because comparison, join, and aggregation operations are then reduced to bit arithmetic, which substantially reduces the processing time. Bitmap indexing leads to significant reductions in space and input-output I/O, since a string of characters can be represented by a single bit. For higher cardinality domains, the method can be adapted using compression techniques. The join indexing method gained popularity from its use in relational database query processing. Traditional indexing maps the value in a given column to a list of rows having that value. In contrast, join indexing registers the joinable rows of two relations from a relational database. The star schema model of data warehouses makes join indexing attractive for cross-table search because the linkage between a fact table and its corresponding dimension tables comprises the fact table's foreign key and the dimension table's primary key. Join indexing maintains relationships between attribute values of a dimension, that is, within a dimension table, and the corresponding rows in the fact table. Join indices may span multiple dimensions to form composite join indices. We can use join indices to identify subcubes that are of interest. To further speed up query processing, the join indexing and the bitmap indexing methods can be integrated to form bitmapped join indices. Efficient processing of OLAP queries. The purpose of materializing cuboids and constructing OLAP index structures is to speed up query processing in data cubes. Given materialized views, query processing should proceed as follows. Determine which operation should be performed on the available cuboids. This involves transforming any selection, projection, roll-up, group by, and drill-down operations specified in the query into corresponding SQL and or OLAP operations. For example, slicing and dicing a data cube may correspond to a selection and or projection operations on a materialized cuboid. Determine to which materialized cuboids the relevant operation should be applied. This involves identifying all of the materialized cuboids that may potentially be used to answer the query, pruning the set using knowledge of dominance relationships among the cuboids, estimating the costs of using the remaining materialized cuboids, and selecting the cuboid with the least cost.
How would the cost of each cuboid compare if used to process the query? It is likely that using cuboid 1 would cost the most because both item name and city are at the lower level than the brand and provinces or state concept specified in the query. If there are not many values associated with items in the cube, but there are several item names for each brand, then cube 3 will be smaller than cube 4, and thus cube 3 should be chosen to process the query. However, if efficient indices are available for cube 4, then cube 4 may be a better choice. Therefore, some cost-based estimate is required to decide which set of cuboids should be selected for query processing.
OLAP server architectures. ROLAP versus MOLAP versus HOLAP. Implementations of a warehouse server for OLAP processing include the following. Relational OLAP, ROLAP servers. These are the intermediate servers that stand in between a relational backend server and client front-end tools. They use a relational or extended relational DBMS to store and manage warehouse data and OLAP middleware to support missing pieces. ROLAP servers include optimization for each DBMS backend, implementation of aggregation navigation logic, and additional tools and services. ROLAP technology tends to have greater scalability than MOLAP technology. The DSS server of MicroStrategy, for example, adopts the ROLAP approach. Multidimensional OLAP, MOLAP servers. These servers support multidimensional data views through array-based multidimensional storage engines. They map multidimensional views directly to data cube array structures. The advantage of using a data cube is that it allows fast indexing to pre-computed summarized data. In such cases, sparse matrix compression techniques should be explored. Many MOLAP servers adopt a two-level storage representation to handle dense and sparse data sets. Denser subcubes are identified and stored as array structures, whereas sparse subcubes employ compression technology for efficient storage utilization. Hybrid OLAP, HOLAP servers. The hybrid OLAP approach combines ROLAP and MOLAP technology, benefiting from the greater scalability of ROLAP and the faster computation of MOLAP. For example, a HOLAP server may allow large volumes of detailed data to be stored in a relational database, while aggregations are kept in a separate MOLAP store. The Microsoft SQL Server 2000 supports a hybrid OLAP server. Specialized SQL servers. To meet the growing demand of OLAP processing in relational databases, some database system vendors implement specialized SQL servers that provide advanced query language and query processing support for SQL queries over star and snowflake schemas in the read-only environment. How are data actually stored in ROLAP and MOLAP architectures? The base fact table stores data at the abstraction level, indicated by the join keys in the schema for the given data cube. Aggregated data can also be stored in fact tables, referred to as summary fact tables. Some summary fact tables store both base fact table data and aggregated data. Alternatively, separate summary fact tables can be used for each abstraction level to store only aggregated data. Measures. Measures, their categorization and computation. A multidimensional point in the data cube space can be defined by a set of dimension-value pairs. For example, time is Q1, location, Vancouver, and item, computer. A data cube measure is a numeric function that can be evaluated at each point in the data cube space. A measure value is computed for a given point by aggregating the data corresponding to the respective dimension, value pairs, defining the given point. Measures can be organized into three categories: distributive, algebraic, and holistic, based on the kind of aggregate functions used. Distributive. An aggregate function is distributive if it can be computed in a distributed manner as follows. Suppose the data are partitioned into n sets. We apply the function to each partition, resulting in n aggregate values. If the result derived by applying the function to the n aggregate values is the same as that derived by applying the function to the entire data set without partitioning, the function can be computed in a distributed manner. For example, sum can be computed for a data cube by first partitioning the cube into a set of subcubes, computing sum for each subcube, and then summing up the counts obtained for each subcube. Hence, sum is a distributive aggregate function. For the same reason, count, minimum, and maximum are distributive aggregate functions. By treating the count value of each non-empty base cell as 1 by default, count of any cell in a cube can be viewed as a sum of the count values of all of its corresponding child cells in its subcube. Thus, count is distributive. A measure is distributive if it is obtained by applying a distributive aggregate function. Distributive measures can be computed efficiently because of the way the computation can be partitioned. Algebraic. An aggregate function is algebraic if it can be computed by an algebraic function with m arguments, where m is a bounded positive integer, each of which is obtained by applying a distributive aggregate function. For example, average can be computed by sum, count, where both sum and count are distributive aggregate functions. Similarly, it can be shown that min and max, which find the n minimum and n maximum values, respectively, in a given set, and standard deviation are algebraic aggregate functions. A measure is algebraic if it is obtained by applying an algebraic aggregate function. Holistic. An aggregate function is holistic if there is no constant bound on the storage size needed to describe a subaggregate. That is, there does not exist an algebraic function with m arguments, where m is a constant that characterizes the computation. Common examples of holistic functions include median, mode, and rank. A measure is holistic if it is obtained by applying a holistic aggregate function. Most large data cube applications require efficient computation of distributive and algebraic measures. Many efficient techniques for this exist. In contrast, it is difficult to compute holistic measures efficiently. Efficient techniques to approximate the computation of some holistic measures, however, do exist. Notice that most of the current data cube technology confines the measures of multidimensional databases to numeric data. However, measures can also be applied to other kinds of data, such as spatial, multimedia, or text data. Multidimensional data model, data cube. Data cube, a multidimensional data model. A data cube allows data to be modeled and viewed in multiple dimensions. It is defined by dimension and facts. Dimensions are the perspectives or entities with respect to which an organization wants to keep records. Each dimension may have a table associated with it, called the dimension table, which further describes the dimension. Dimension tables can be specified by users or experts, or automatically generated and adjusted based on data distributions. A multi-dimensional data model is typically organized around a central theme, such as sales. This theme is represented by a fact table. Facts are numeric measures. Think of them as the quantities by which we want to analyze relationships between dimensions. The fact table contains the names of the facts or measures, as well as keys to each of the related dimension tables. The actual physical storage of data may differ from its logical representation. The important thing to remember is that data cubes are n-dimensional and do not confine data to 3D. Given a set of dimensions, we can generate a cuboid for each of the possible subsets of the given dimensions. The result would form a lattice of cuboids, each showing the data at a different level of summarization or grouped by. The lattice of cuboids is then referred to as data cube. Figure shows a lattice of cuboids forming a data cube for the dimensions time, item, location, and supplier. The cuboid that holds the lowest level of summarization is called the base cuboid. The 0D cuboid, which holds the highest level of summarization, is called the apex cuboid. In our example, this is the total sales, or dollars sold, summarized over all 4 dimensions. The apex cuboid is typically denoted by all. OLAP operation on multidimensional data model. In the multidimensional model, data are organized into multiple dimensions, and each dimension contains multiple levels of abstraction defined by concept hierarchies. This organization provides users with the flexibility to view data from different perspectives. A number of OLAP data cube operations exist to materialize these different views, allowing interactive querying and analysis of the data at hand. Hence, OLAP provides a user-friendly environment for interactive data analysis. Example for OLAP operations. The cube contains the dimensions location, time, and item, where location is aggregated with respect to city values, time is aggregated with respect to quarters, and item is aggregated with respect to item types. To aid in our explanation, we refer to this cube as the central cube. The measure displayed is dollars sold in thousands. For improved readability, only some of the cube's cell values are shown. The data examined are for the cities of Chicago, New York, Toronto, and Vancouver. Roll-up. The roll-up operation, also called the drill-up operation by some vendors, performs aggregation on a data cube either by climbing up a concept hierarchy for a dimension or by dimension reduction. This hierarchy was defined as a total order: street, city, province, or state, country. The roll-up operation shown aggregates the data by ascending the location hierarchy from the level of city to the level of country. In other words, rather than grouping the data by city, the resulting cube groups the data by country. When roll-up is performed by dimension reduction, one or more dimensions are removed from the given cube. For example, consider a sales data cube containing only the location and time dimensions. Roll-up may be performed by removing, say, the time dimension, resulting in an aggregation of the total sales by location rather than by location and by time. Drill down. Drill down is the reverse of roll-up. It navigates from less detailed data to more detailed data. Drill down can be realized by either stepping down a concept hierarchy for a dimension or introducing additional dimensions. Drill down occurs by descending the time hierarchy from the level of quarter to the more detailed level of month. The resulting data cube details the total sales per month rather than summarizing them by quarter. Because a drill down adds more detail to the given data, it can also be performed by adding new dimensions to a cube. For example, a drill down on the central cube or figure can occur by introducing an additional dimension such as customer group. Slice and dice. The slice operation performs a selection on one dimension of the given cube, resulting in a subcube. The dice operation defines a subcube by performing a selection on two or more dimensions. A dice operation on the central cube based on the following selection criteria that involve three dimensions: location, Toronto or Vancouver, time, Q1 or Q2, and item, home entertainment or computer. Pivot, rotate. Pivot, also called rotate, is a visualization operation that rotates the data axis in view to provide an alternative data presentation. Other examples include rotating the axis in a 3D cube or transforming a 3D cube into a series of 2D planes. Other OLAP operations. Some OLAP systems offer additional drilling operations. For example, drill across executes queries involving across more than one fact table. The drill through operation uses relational SQL facilities to drill through the bottom level of a data cube down to its backend relational tables. Other OLAP operations may include ranking the top n or bottom n items in lists, as well as computing moving averages, growth rates, interests, internal return rates, depreciation, currency conversions, and statistical functions. OLAP offers analytical modeling capabilities, including a calculation engine for deriving ratios, variance, and so on, and for computing measures across multiple dimensions. It can generate summarizations, aggregations, and hierarchies at each granularity level and at every dimensional intersection. OLAP also supports functional models for forecasting, trend analysis, and statistical analysis. In this context, an OLAP engine is a powerful data analysis tool. Relationship between data warehouse and data mining. Evolution of database technology. Transaction processing systems support the operational level of the organization, possibly integrating needs of different functional areas, ERP. Perform and record the daily transactions necessary to the conduct of the business. Execute simple read-update operations on traditional databases, aiming at maximizing transaction throughput. Their activity is described as OLTP, Online Transaction Processing. Knowledge level systems provide digital support for managing documents, office automation, user cooperation and communication, groupware, storing and retrieving information, content distribution, automation of business procedures, workflow management. Management level systems support planning, controlling, and semi-structured decision-making at management level by providing reports and analysis of current and historical data. Executive support systems support unstructured decision-making at the strategic level of the organization. OLAP, Online Analytical Processing. Reporting based on multidimensional data analysis. Read-only access on repositories of moderate large size, typically data warehouses, aiming at maximizing response time. Data mining. Discovery of novel implicit patterns from possibly heterogeneous data sources. Use a mix of sophisticated statistical and high-performance computing techniques. Data warehouse. Database with the following distinctive characteristics. Separate from operational databases. Subject-oriented. Provides a simple, concise view on one or more selected areas in support of the decision process. Constructed by integrating multiple heterogeneous data sources. Contains historical data. Spans a much longer time horizon than operational databases. Mostly read-only access. Periodic, infrequent updates. Types of data warehouses. Enterprise warehouse covers all areas of interest for an organization. Data mart covers a subset of corporate-wide data that is of interest for a specific user group, for example, marketing. Virtual warehouse offers a set of views constructed on demand on operational databases. Some of the views could be materialized or pre-computed. Figure shows multi-tier architecture. Multidimensional logical model. Data are organized around one or more fact tables. Each fact table collects a set of homogeneous events, facts characterized by dimensions and dependent attributes. For example, sales at a chain of stores can be represented by the table shown. Each dimension can in turn consist of a number of attributes. In this case, the value in the fact table is a foreign key referring to an appropriate dimension table. Star schema. Conceptual star schema, ER model. OLAP server architectures. They are classified based on the underlying storage layouts. ROLAP, Relational OLAP, uses relational DBMS to store and manage warehouse data, that is, table-oriented organization and specific middleware to support OLAP queries. MOLAP, Multidimensional OLAP, uses array-based data structures and pre-computed aggregated data. It shows higher performance than OLAP, but may not scale well if not properly implemented. HOLAP, Hybrid OLAP, ROLAP approach for low-level raw data, MLOP approach for higher-level data aggregations. Cube operator in SQL. Select product, period, region, sum, total sales from fact table. Group by product, period, region with cube. Rollup, partial cube operator in SQL. Select product, period, region, sum, total sales from fact table. Group by product, period, region with rollup. Reduces the complexity from exponential to linear in the number of dimensions. It is equivalent to computing the following subset of the lattice of cuboids. Data mining. Data explosion. Tremendous amount of data accumulated in digital repositories around the world, such as databases, data warehouses, web, etc. Figure represents knowledge discovery in databases. Typologies of input data. Unaggregated data, records, transactions, aggregated data, summaries, spatial geographic data, data from time series databases, text, video, audio, web data. Process of discovering interesting patterns of knowledge from a typically large amount of data stored either in databases, data warehouses, or other information repositories. Interesting, non-trivial, implicit, previously unknown, potentially useful. Alternative names: knowledge discovery extraction, information harvesting, business intelligence. In fact, data mining is a step of the more general process of knowledge discovery in databases, or KDD. Interestingness measures. Purpose: filter irrelevant patterns to convey concise and useful knowledge. Certain data mining tasks can produce thousands of millions of patterns, most of which are redundant, trivial, or irrelevant. Objective measures: based on statistics and structure of patterns, that is, frequency counts. Subjective measures: based on users' belief about the data. Patterns may become interesting if they conform or contradict a user's hypothesis, depending on the context. Interestingness measures can be employed both after and during the pattern discovery. In the latter case, they improve the search efficiency. Multidisciplinarity of data mining. Data mining problems. Association rules. Discovery of rules X, Y. Objects that satisfy condition X are also likely to satisfy condition Y. The problem first found application in market basket or transaction data analysis, where objects are transactions and conditions are containment of certain item sets. Statement of the problem: I, set of items, D, set of transactions. T belongs to D, then T is a subset of I. For an item set, X is a subset of I. Suppose X equals fraction or number of transactions containing X. Association rule: X minus Y implies Y, with Y being a proper set of X which is a subset of I. Support equals support X. Confidence equals support X divided by support X minus Y. Problem: find all association rules with support greater or equal to min support and confidence greater or equal to min confidence. Sequential patterns. Discovery of frequent subsequences in a collection of sequences, sequence database, each representing a set of events occurring at subsequent times. The ordering of the events in the subsequences is relevant. Problem: given a set of sequences, find the complete set of frequent subsequences. A sequence EF, AB, DF, C, B. An element may contain a set of items. Items within an element are unordered and are listed alphabetically. A, BC, C, D is a subsequence of A, ABC, AC, D, CF. For min support equals 2, ABC is a frequent subsequence. A sequence database is shown on screen. Applications: marketing, natural disaster forecast, analysis of web log data, and DNA analysis. Classification or regression: discovery of a model or function that maps objects into predefined classes, classification, or into suitable values, regression. The model function is computed on a training set, supervised learning. Statement of the problem: training set T equals T1 ... Tn set of n examples. Each example Ti, characterized by m features, Ti A1 ... Tim, belongs to one of k classes. Ci is to 1 ik. Goal: from the training data, find a model to describe the classes accurately and synthetically using the data's features. The model will then be used to assign class labels to unknown, previously unseen records. Applications: classification of potential customers for credit approval, risk prediction, selective marketing, performance prediction based on selected indicators, medical diagnosis based on symptoms or reactions to therapy. Observations: features can be either categorical if belonging to unordered domains, such as car type, or continuous if belonging to ordered domains, such as age. The class could be regarded as an additional attribute of the examples which we want to predict. Classification versus regression. Classification builds models for categorical classes. Regression builds models for continuous classes. Several types of models exist: decision trees, neural networks, Bayesian, or statistical classifiers. Classification using decision trees. Definition: decision tree for a training set T. Classification process. Labeled tree. Each internal node V represents a test on a feature. The edges from V to its children are labeled with mutually exclusive results of the test. Each leaf W represents a subset of examples of T whose features values are consistent with the test results found along the path from the root to W. The leaf is labeled with the majority class of the examples it contains. Clustering. Grouping objects into classes with the objectives of maximizing intra-class similarity and minimizing inter-class similarity. Unsupervised learning. Statement of the problem. Given n objects, each characterized by p attributes, also known as variables. Group the objects into k clusters featuring high intra-cluster similarity, low inter-cluster similarity. Remark: clustering is an instance of unsupervised learning or learning by observations as opposed to supervised learning or learning by examples, known as classification. Several types of clustering problems exist depending on the specific input-output requirements and on the notion of similarity. The number of clusters k may be provided in input or not. As output, for each cluster one may want a representative object or a set of aggregate measurements or the complete set of objects belonging to the cluster. Distance-based clustering. Similarity of objects is related to some kind of geometric distance. Conceptual clustering. A group of objects forms a cluster if they define a certain concept. Applications. Marketing. Identify groups of customers based on their purchasing patterns. Biology. Categorize genes with similar functionalities. Image processing. Clustering of pixels. Web. Clustering of documents in meta search engines. GIS. Identification of areas of similar land use. Challenges. Scalability. Strategies to deal with very large data sets. Variety of attribute types. Defining a good notion of similarity is hard in the presence of different types of attributes and/or different scales of values. Variety of cluster shapes. Common distance measures provide only spherical clusters. Noisy data. Outliers may affect the quality of the clustering. Sensitivity to input ordering. The ordering of the input data should not affect the output or its quality. Main distance-based clustering methods. Partitioning methods. Create an initial partition of the objects into k clusters and refine the clustering using iterative relocation techniques. A cluster is represented either by the mean value of its component objects or by a centrally located component object, midoid. Hierarchical methods. Start with all objects belonging to a distinct clusters and then successfully merge the pair of closest clusters objects into one single cluster, agglomerative approach. Or start with all objects belonging to one cluster and successively split up a cluster into smaller ones, divisive approach. Stars, snowflakes, and fact constellations. Schemas for multidimensional data models. The entity relationship data model is commonly used in the design of relational databases, where a database schema consists of a set of entities and the relationships between them. Such a data model is appropriate for online transaction processing. A data warehouse, however, requires a concise, subject-oriented schema that facilitates online data analysis. The most popular data model for a data warehouse is a multi-dimensional model, which can exist in the form of a star schema, a snowflake schema, or a fact constellation schema. Star schema. The most common modeling paradigm is the star schema, in which the data warehouse contains a large central table, fact table, containing the bulk of the data with no redundancy, and a set of smaller attendant tables, dimension tables, one for each dimension. This schema graph resembles a starburst with the dimension tables displayed in a radial pattern around the central fact table. Example for star schema. Sales are considered along 4 dimensions: time, item, branch, and location. The schema contains a central fact table for sales that contains keys to each of the 4 dimensions, along with 2 measures, dollars sold and units sold. To minimize the size of the fact table, dimension identifiers, for example, time key and item key, are system-generated identifiers. Notice that in the star schema, each dimension is represented by only one table, and each table contains a set of attributes. For example, the location dimension table provides an attribute set: location, key, street, city, province, state, or country. This constraint may introduce some redundancy. Entries for such cities in the location dimension table will create redundancy among the attributes province or state and country. Moreover, the attributes within a dimension table may form either a hierarchy, total order, or a lattice, partial order. Snowflake schema. The snowflake schema is a variant of the star schema model, where some dimensional tables are normalized, thereby further splitting the data into additional tables. The resulting schema graphs forms a shape similar to a snowflake. The major difference between the snowflake and the star schema models is that the dimension tables of the snowflake model may be kept in normalized form to reduce redundancies. Such a table is easy to maintain and saves storage space. However, this space savings is negligible in comparison to the typical magnitude of the fact table. Furthermore, the snowflake structure can reduce the effectiveness of browsing, since more joins would be needed to execute a query. Consequently, the system performance may be adversely impacted. Hence, although the snowflake schema reduces redundancy, it is not as popular as the star schema in data warehouse design. Example for snowflake schema. In a snowflake schema for all electronic sales, the sales fact table is identical to that of the star schema. The main difference between the two schemas is in the definition of dimension tables. The single dimension table for an item in the star schema is normalized in the snowflake schema, resulting in new item and supplier tables. For example, the item dimension table now contains the attributes item key, item name, brand, type, and supplier key, where supplier keys link to the supplier dimension table containing supplier key and supplier type information. Similarly, the single dimension table for location in the star schema can be normalized into 2 new tables, location and city. The city key in the new location table links to the city's dimension. Notice that, when desirable, further normalization can be performed on the province or state and country in the snowflake schema. Fact constellation. Sophisticated applications may require multiple fact tables to share dimension tables. This kind of schema can be viewed as a collection of stars, and hence it is called a galaxy schema or a fact constellation. Example for fact constellation. A fact constellation schema specifies two fact tables, sales and shipping. The sales table definition is identical to that of the star schema. The shipping table has 5 dimensions or keys: item key, time key, shipper key, from location and to location, and 2 measures: dollars cost and units shipped. A fact constellation schema allows dimension tables to be shared between fact tables. For example, the dimension tables for time, item, and location are shared between the sales and the shipping fact tables. The figure shows fact constellation schema of sales and shipping data warehouse. In data warehousing, there is a distinction between data warehouse and a data mart. A data warehouse collects information about subjects that span the entire organization, such as customers, items, sales, assets, and personnel, and thus its scope is enterprise-wide. For data warehouses, the fact constellation schema is commonly used since it can model multiple interrelated subjects. A data mart, on the other hand, is a department subset of the data warehouse that focuses on selected subjects, and thus its scope is department-wide. For data marts, the star or snowflake schema is commonly used since both are geared toward modeling single subjects, although the star schema is more popular and efficient. Types of OLAP servers. Logically, OLAP servers present business users with multidimensional data from data warehouses or data marts without concerns regarding how or where the data are stored. However, the physical architecture and implementation of OLAP servers must consider data storage issues. Implementations of a warehouse server for OLAP processing include the following: Relational OLAP, ROLAP servers. These are the intermediate servers that stand in between a relational backend server and a client front-end tools. They use a relational or extended relational DBMS to store and manage warehouse data and OLAP middleware to support missing pieces. ROLAP servers include optimization for each DBMS backend, implementation of aggregation navigation logic, and additional tools and services. ROLAP technology tends to have greater scalability than MOLAP technology. The DSS server or MicroStrategy, for example, adopts the ROLAP approach. Specialized SQL servers. To meet the growing demand of OLAP processing in relational databases, some database system vendors implement specialized SQL servers that provide advanced query language and query processing support for SQL queries over star and snowflake schemas in a read-only environment. Multidimensional OLAP, MOLAP servers. These servers support multidimensional data views through array-based multidimensional storage engines. They map multidimensional views directly to data cube array structures. The advantage of using a data cube is that it allows fast indexing to pre-computed summarized data. Note that with multidimensional data stores, the storage utilization may be low if the data set is sparse. In such cases, sparse matrix compression techniques should be explored. Many MOLAP servers adopt a two-level storage representation to handle dense and sparse data sets. Denser subcubes are identified and stored as array structures, whereas sparse subcubes employ compression technology for efficient storage utilization. Hybrid OLAP, HOLAP servers. The hybrid OLAP approach combines ROLAP and MOLAP technology, benefiting from the greater scalability of ROLAP and the faster computation of MOLAP. For example, a HOLAP server may allow large volumes of detailed data to be stored in a relational database, while aggregations are kept in a separate MOLAP store. The Microsoft SQL Server 2000 supports a hybrid OLAP server. Data storage in ROLAP. As its name implies, ROLAP uses relational tables to store data for online analytical processing. The fact table associated with a base cuboid is referred to as a base fact table. The base fact table stores data at the abstraction level indicated by the join keys in the schema for the given data cube. Aggregated data can also be stored in fact tables referred to as summary fact tables. Some summary fact tables store both base fact table data and aggregated data. Alternatively, separate summary fact tables can be used for each abstraction level to store only aggregated data. Example, a ROLAP data store. The schema is a record identifier, RID, item, and so on, up to day, month, quarter, year, dollar sold, where day, month, quarter, and year define the sales date and dollar sold is the sales amount. Consider the tuples with an RID of 1001 and 1002 respectively. The data of these tuples are at the base fact level, where the sales dates are October 15, 2010 and October 23, 2010 respectively. Consider the tuple with an RID of 5001. This tuple is at a more general level of abstraction than the tuples 1001 and 1002. The day value has been generalized to all so that the corresponding time value is October 2010. That is, the dollars sold amount shown is an aggregation representing the entire month of October 2010 rather than just October 15 or 23, 2010. The special value all is used to represent subtotals in summarized data. MOLAP uses multidimensional array structures to store data for online analytical processing. Most data warehouse systems adopt a client-server architecture. A relational data store always resides at the data warehouse, data mart, server site. A multidimensional data store can reside at either the database server site or the client site. A single table for base and summary facts is presented. Conclusion. In this chapter, we have covered the following in detail. Concepts of data warehouse, difference between operational database system and data warehouse, multidimensional data model, data cube, stars, snowflakes, fact schemas for multidimensional database, measures, concept hierarchies, OLAP operation on multidimensional data model, data warehouse architecture, types of OLAP servers, life cycle of data warehouse implementation, relationship between data warehouse and data mining.